Hi, I'm Elaine, and I'll be guiding you through this module. The next 2 slides show the objectives for this course. So, what is chemical bonding? Chemical bonding occurs when 2 or more atoms combine, by gaining, losing, or sharing electrons so that an entirely new substance is produced. This new substance has different physical and chemical properties than its component elements. Remember from the last module, the only electrons involved in bonding are the valence electrons, those in the outermost shell. Atoms want to gain, lose or share electrons so that their valence shells are full and they become chemically stable. For most elements, this means having 8 valence electrons. But for the smallest atoms, hydrogen, helium, lithium and beryllium, they are happy having only 2 valence electrons. In this module, we'll be looking at 3 types of chemical bonding: ionic, covalent, and metallic. The first type of bonds we'll discuss are ionic bonds. These bonds are formed when electrons are gained or lost. One atom, usually a metal, loses 1 or more electron. Another atom, usually a nonmetal, gains 1 or more electrons. In the process, both elements have a filled outer shell. For example, take sodium and chlorine. Since sodium has only 1 valence electron, it has a tendency to give up that electron. Once it does that, the outer shell contains 8 electrons. Recall from the last module, this loss of an electron gives sodium a positive charge. Chlorine, on the other hand, with 7 valence electrons, would like to gain an electron to become stable. When chlorine gains an electron, it becomes a negative ion. Remember, the charged sodium and chlorine atoms are called ions. Ions of opposite charges attract each other and form ionic bonds. In this case, the attraction of sodium and chlorine form a molecule called sodium chloride, better known as table salt. The force that holds ions together in an ionic bond is the electrostatic attraction between oppositely charged particles. Recall from last module, elements in groups 1 and 2, which are metals, are electron donors. Nonmetals from groups 6 and 7 are electron grabbers. Elements from these extreme ends of the table usually form ionic bonds when they interact. For example, how would magnesium and oxygen react to form an ionic bond? Notice that magnesium is in group 2. So it has 2 valence electrons. Ideally, magnesium wants to lose those 2 electrons. So it will have 8 valence electrons. Oxygen is in group 6. So it has 6 valence electrons. And it needs to gain 2 electrons to get to 8. So magnesium transfers its 2 valence electrons to oxygen, forming a magnesium ion and an oxide ion. The resulting ions are electrostatically attracted to one another, forming an ionic bond. This results in a brand new substance, magnesium oxide. Covalent bonds are bonds that are formed by atoms sharing electrons to achieve a full outer shell. Covalent bonding occurs when neither atom has sufficient strength to completely remove the other atom's electrons. The atoms share electrons, and both atoms achieve a stable configuration. A hydrogen atom with 1 valence electron needs 1 additional electron to fill its outer shell, which holds 2. An oxygen atom has 6 valence electrons and needs 2 additional electrons to fill its outer shell, which holds 8. As the hydrogen and oxygen atoms collide, covalent bonding occurs through the sharing of electrons. By sharing with the oxygen, hydrogen has achieved its goal of filling its outer energy level with 2 electrons. Oxygen, on the other hand, now has 7 valence electrons, still one short of a stable octet condition. This stable octet condition can be achieved by sharing an electron with another hydrogen atom.
And that's what I call high-quality duo.
A carbon atom has 4 valence electrons. Therefore, carbon needs 4 more electrons to fill its outer shell and become stable. To achieve this, carbon can share with other atoms. If 1 carbon and 4 hydrogen atoms come together and share their electrons, carbon has filled its valence shell and so have the 4 hydrogens. The result is CH4, methane gas. The force that holds atoms together in covalent bonds are the overlapping or intertwined electron clouds of the atoms. Some elements are more stable when they share electrons with each other. They are called diatomic elements. Diatomic elements are elements that cannot exist by themselves. 2 common examples are hydrogen, H2, and oxygen, O2. There are 7 such elements. You do not need to memorize them. Metallic bonding occurs in metals as a result of the loosely held electrons in the valence shells of the metal atoms. These electrons are delocalized, meaning they are free to move around. In other words, atoms are surrounded by a sea of electrons. Free-flowing electrons is the reason metals can conduct heat and electricity. Recall from Chapter 1 that metals are malleable, meaning they can be molded into different shapes, and ductile, meaning they can be stretched into wires. No matter what shape the metal takes, the free-flowing electrons will conform to that shape. Why are metals so shiny? Because electrons in the sea have a wide range of possible energies. Therefore they can absorb and re-emit many wavelengths of light. There are 3 basic laws of chemistry. They are: law of conservation of mass, law of definite proportions, and the law of multiple proportions. The law of the conservation of mass states that matter can neither be created nor destroyed in a chemical reaction. You start and end with the same amount. In this example of wood burning, the amount of wood, the reactant, is equal to the amount or product, ash and smoke. Just like in a recipe, the weight or mass of the ingredients must equal the weight or mass of the final product. The total mass of these beakers does not change despite a chemical reaction having taken place. The law of conservation of mass says the total mass of the reactants and the total mass of the products must be the same. The law of definite proportions states that a compound always contains elements in certain definite proportions by weight. For example, water, H2O, is always composed of 2 parts hydrogen and 1 part oxygen. The law of multiple proportions states that elements may combine in more than one set of proportions and that each set of proportions corresponds to a different compound. In addition, the differences in the sets of proportions will be in small whole number ratios of one of the combining atoms. For example, carbon and oxygen form 2 compounds, namely carbon dioxide and carbon monoxide. Note there is 1 carbon atom and 1 oxygen atom in the carbon monoxide, but there are 2 oxygen atoms in carbon dioxide. Chemical formulas show the kinds and numbers of atoms in the smallest representative unit of a substance. We've already talked about many of these. Formulas show which elements make up a molecule and how many elements are in that molecule. The subscripts show how many atoms are in the molecule. Water, H2O, contains 2 atoms of hydrogen. The number that is placed before the formula is called the coefficient. This indicates how many molecules are present. Some ions are actually polyatomic, meaning multiple atoms, ions. The whole group is tightly bonded together and behave like one atom. They form a positive or negative ion together. Here are 2 examples of positive polyatomic ions, ammonium with a charge of +1, and hydronium, also with a charge of +1. Often a metal or a halogen will combine with one of these polyatomic ions. Here are 2 you may be familiar with, sodium hydrogen carbonate, or baking soda, and sodium hydroxide, also known as Drano. In compounds containing polyatomic ions, parentheses are used to enclose the polyatomic ion when more than one of these ions is contained in the compound. A numerical subscript outside the parenthesis indicates the number of polyatomic ions in the formula. That subscript is a multiplier applied to all atoms enclosed in the parentheses. This compound is called aluminum nitrate. How many atoms of each element are in this compound? The solution is on the next slide. First, let's look at aluminum. Remember, if there is no number subscript, we assume the number 1. So there is only 1 aluminum atom. Nitrogen is in the parentheses, so however many nitrogen atoms are in the parentheses must be multiplied by the number outside the parentheses. Therefore, we multiply 1 times 3. So we have a total of 3 nitrogen atoms. Finally, oxygen is within the parentheses, and there are 3 oxygen atoms. So we must multiply 3 times 3, so we have a total of 9 oxygen atoms. A chemical reaction is described by a chemical equation, an expression that gives the identities and quantities of the substances involved in a reaction. A chemical equation shows the starting materials, the reactants, on the left, and the final materials, the products, on the right, separated by an arrow. This equation describing the formation of sodium chloride, table salt, is read as 2 molecules of sodium, combined with 1 molecule of chlorine, produces, or yields, 2 molecules of sodium chloride. Remember, chlorine is one of those 7 diatomic elements that exists in nature as Cl2 and not Cl. Sometimes a chemical equation will display additional information such as the states of the elements, solid, liquid or gas, whether the reaction takes place in water, aqueous, the presence of heat, to be discussed later, and if a catalyst is added, also to be discussed later. Given this new information, the last equation for the formation of table salt could be more accurately described as 2 molecules of sodium in its solid form combines with 1 molecule of chlorine gas to form 2 molecules of sodium chloride in its solid form. Now let's discuss the concept of a balanced equation. A balanced equation shows the amounts of reactants and products involved in a reaction. In this course, you won't have to balance an equation yourself, you just need to be familiar with the concept and significance of a balanced equation. A balanced equation also shows the relative amounts, or mole ratio, of reactants and products. In the example, the ratio of carbon to O2 to CO2 is 1 to 1 to 1. 1 mole carbon to 1 mole of O2 gives you 1 mole of CO2. So how do we use this? Here's a basic recipe for chili. Notice the yield is 4 servings. What if we needed a bigger batch, say, 20 servings? How would we adjust this recipe to make 20 servings of chili? Since we need 5 times more than the recipe, that yields only 4 servings, we simply multiply each ingredient by 5. So what does making chili have to do with chemistry? Here is the basic recipe for sodium chloride, table salt, NaCl. 2 moles of sodium plus 1 mole of chloride yields 2 moles of sodium chloride. So, if we wanted 10 moles of sodium chloride instead of 2, how many moles of sodium and chlorine would we need? Well, we know that 10 is 5 times more than 2, or we could just divide 10 by 2 to get 5. So we need 5 times more of each reactant to get the required 10 moles of sodium chloride. Here's an example using the formula for water. Fill in the blanks with the correct number, then hit submit. In chemical reactions, sometimes energy needs to be supplied to start the reaction to create new products. And sometimes when new products are created, energy is released. This energy is usually in the form of heat. Delta H, the heat of reaction, is the amount of heat released or absorbed during a reaction. A reaction where energy is released is called an exothermic reaction. A reaction where energy is absorbed is called an endothermic reaction. Remember, exo exit, endo enter. Here are some examples of exothermic and endothermic reactions. Please don't try any of these at home. In fact, don't try them at anyone's home. Breaking bonds is always an endothermic process. That is because energy must be added to the system to overcome the attractive forces holding atoms together. Forming bonds is always an exothermic process. Sometimes the chemical reaction needs a kick to get started. Activation energy is defined as the minimum amount of energy required to start a chemical reaction. Energy required to get you over the hump. Reaction rates are affected by the nature of the reactants, the surface area of the reactants, the concentration of the reactants, the temperature of the environment, and the presence of a catalyst. When we talk about the nature of the reactants, considerations include how reactive are the reactants, and how strong are the bonds that must be broken in order for the reaction to occur. Surface area affects the reaction rate of reactions involving solids. Since reactions take place on the surface of solids, increasing the surface area exposes more atoms to the other reactant. This also increases the number of collisions and speeds the reaction. Concentration is only a consideration with liquids and gases. Increasing the number of atoms of one or both reactants increases the number of collisions. More of the reacting particles are present in the given volume, results in an increased reaction rate. Increasing the temperature of the environment increases particle energy. Decreasing temperature decreases particle energy. Faster moving particles collide more often. Therefore, more particles achieve or exceed the minimum activation energy needed to complete the reaction. A catalyst is a substance that changes the reaction rate, but does not get consumed in the reaction. A catalyst provides an alternative pathway or reaction mechanism for the reaction, and also lowers the activation energy needed to start the reaction. Some reactions are reversible. A reversible reaction is one in which the products can react to reform the reactants. Reversible reactions are indicated by double arrows between products and reactants. Here is an example of a reversible reaction. This is red. Liquid mercury reacts with oxygen gas when heated. Delta is the symbol for heat, to form solid mercury, 2, oxide. Once formed, some of the product decomposes to form mercury and oxygen. Chemical equilibrium is the state in which the rate of the forward and reverse reactions are exactly equal. 3 factors will stress or disturb a system and shift equilibrium. Change in concentration, change in pressure, for gas systems only, and change in temperature. Le Chatelier's principle, named after French chemist Henri-Louis Le Chatelier, explains the behavior of an equilibrium system when it is subject to changes. The principle states, if a system at equilibrium is subjected to a stress change, the equilibrium is shifted in the direction that relieves the stress. Afterward, the system will re-establish equilibrium under the new conditions. Consider this hypothetical reversible reaction. If more reactant is added, A and B, to the left side, the test tube that was resting in the middle of the seesaw is now stressed to the left and wants to get back to the middle. So the test tube creates more product, C and D, thus shifting the system to the right until he's comfortably in the middle again. He's at equilibrium. What if we were to add more product? That would stress the system, the test tube, to the right, so to relieve that stress, more reactant would have to be added, thus shifting the system to the left. If we take away some product, the system would be again stressed to the left. So to relieve that stress, more product would have to be added, shifting the system to the right. Now let's look at an example using a real reversible reaction. The formation of hydrogen iodide from hydrogen and iodine. Increasing the concentration of a reactant either H2 or I2 will stress the system to the left, so according to Le Chatelier's principle, to relieve that stress, the reaction will shift to the right, to create more product. That's because the extra concentration needs to be used up to relieve stress. Increasing the concentration of the product, hydrogen iodide, will stress the system to the right, and shift the reaction to the left, back to the reactants. That's because the excess product needs to be used up, so it's sent back as a reactant. Removing reactants, or decreasing the concentration of the reactants, will shift the reaction back toward the reactants. That's because the product, hydrogen iodide, will try to replenish the reactants that were removed, again, to relieve stress. Finally, removing products, or decreasing concentration of the products, will shift the reaction toward the products. That's because the reactants need to produce more product to make up for what was removed. Before we are able to determine how temperature affects equilibrium, we need to know if the reaction is endothermic or exothermic. In an endothermic reaction, heat is part of the reactants. Remember, in an endothermic reaction, heat must be added or absorbed for a reaction to occur. In an exothermic reaction, heat is part of the products. Remember, in an exothermic reaction, heat is released. So, in either case, If heat is added to the system, equilibrium will shift to the opposite side from where the heat already was. For example, in an exothermic reaction, adding heat to the system shifts equilibrium to the left, toward the reactants. In an endothermic reaction, if heat is added to the system, equilibrium will shift to the right, toward the products. If heat is removed from the system, or cooled, equilibrium will shift to the direction that will provide more heat. Again, remember, in an exothermic reaction, heat is a product, and in an endothermic reaction, heat is a reactant. So, if the reaction is exothermic, cooling shifts equilibrium to the right. If the reaction is endothermic, cooling shifts equilibrium to the left. Pressure changes only affect equilibrium in systems where their reactants and products are gases. If we increase pressure, the reaction shifts to the side with fewer molecules. If we decrease pressure, the reaction shifts to the side with the most molecules. Consider this reaction. Nitrogen gas reacts with hydrogen gas to form ammonia. You'll note that on the left side of this equation, the reactants, there is 1 molecule of nitrogen and 3 molecules of hydrogen. A total of 4 molecules. On the right side, the product side, there are 2 molecules of ammonia, NH3. Therefore, the left side, the reactant side, has the most molecules. Now, let's demonstrate using this closed cylinder where this reaction takes place. Note this cylinder is filled with nitrogen, hydrogen, and ammonia molecules. Notice at initial equilibrium, there are 14 total molecules in the cylinder. Go ahead. Count them. When we increase the pressure by pushing down on the piston, the system comes under stress. The molecules speed up, there is less volume for them to move around, so there are more collisions and more nitrogen molecules are allowed to combine with the hydrogen molecules. The molecules combine with one another to relieve the stress. So, when equilibrium is established under this new pressure, notice there are now only 10 total gas molecules, as some of the nitrogen and hydrogen have combined. Thus, as the rule stated, when you increase pressure, equilibrium shifts to the side with the fewest molecules, in this case the product side. Study this diagram and you can see the exact opposite occurs when pressure in the cylinder is decreased. With greater volume, some of the ammonia molecules reform into hydrogen and nitrogen. Therefore, there are now more molecules. So, as the rule states, decreasing pressure will cause equilibrium to shift to the side with the most molecules, in this case the reactant side. This chart summarizes Le Chatelier's principle.